and today I present one of my data science projects. It's one of the I built it this week. So the main problem of this project is a prediction of the power consumption of the building. I have the data in the Excel file, and this data is about 20,000 rows with all of the data. And this data includes the power consumption from the floor entering of the building. Also, it has the accumulator consumers. It's just consumer, and it has a lot of data, as you see. It's huge Excel file. So what I will do and what I will use for this project. First of all, I just use the GPU card because it's nightmare count of all of this in the CPU. And I just grab all the data, just download of the Excel file, and one of the necessary steps for the data cleaning. I want to, for the particular task, I need to exclude the data from the night hours, from the weekends, and from the celebration days. So I just create a simple mask and do all the cleaning stuff. And I just do this. So then I try to find the target value. I just add up the sum of the four consumers bus. So this one we need to predict. We need to predict the sum of the four of these entering of the buildings. So we examine the data, and good minutes mean that the value is okay, and invalid mean that the data is wrong. We have the special flag on it. Then we just to change the invalid mean to the mean of the series before. We just use the time frame. We just the exam data more, and we just observe the most statistics. I mean the mean, median, min, max, standard deviation, just basic stuff to observe does we have any unnecessary data. And you see on the first entering we have the minus 166,000. So it's nightmare. It's totally wrong data, you see. And we just observe how many data we have. We have 21,100, and all our main idea to save all this data, because later we will use all this data for the time frame predictions, and we don't want to lose any data. It's in my opinion, it's totally necessary stuff. Then we just to see what we do. So here we just change the data with minus to the 0 because it's necessary, because it's totally wrong, and now it's more or less it's good, because if you remember it, we have minimum data here. It was 100 and some thousands, and then we fill the wrong part with the mean again. Yeah, you see. And we just observe again the target sum. The target sum, it's our target which create of the sum of the four entrance of the building. And we just examine this because we create the target sum before we normalize the data, and you see it have the wrong mean. So we recreate this target sum again, but in that time, so all this data in good shape and good value. You see that the mean we have the bigger one, and max and STD it's more or less it's good, not like here that we have the standard deviation more than 2000. And then we create the graph of our consumption, of the power consumption, and you see this graph has this shape. And we create the other, so we create again the target, but in that time it's so the target value will be as sum of the external grid bus for the 4 entries, uh, plus the consumption of the roof, and minus with the accumulator. Because from the condition of this task, we can get the target by the we can get target of the two ways. The first one, from the long formula, we add all this stuff and minus the accumulator, or just sum the 4 entrants. And again, we observe just the simple stats, I mean the math stat, and we create the graph of every part of this long formula, and we see that the consumption have the different shapes. And we do it again, but for the other part of the equation. So then we again to the observe the basic mass stats, graph again and graph again. So the main idea of this extremely huge quantity of the graph to see the shape of the every part of this equation, and will it differ or not. And we see different parts have the little bit different graph, but more or less it's the same. Then we just to observe how many data we lose, and as you see, we just have the data in same quantity, and then we create the target sum. It's our target with the big equation. So we just make sum of the 4 plus minus roof plus accumulator. And in this graph, so we create the graph, and the gray and blue it's same value, but counted over different formulas, and we see that more or less it's our targets it's same. What we do next, we just create the artificial features. We just create the data, week, month, and day, and you see we just take the time and add the artificial features from our data frame. It's the number of days, number of weeks in year, number of months, and week of the day, because we think that the power consumption depends on all this data. And then we create the graph, how is the power consumption changes, depends on the day, on the weeks, and on the years, and you see that here. And more or less it has the some meaningful. Then we create the histogram of the distribution of our target, and we see that it has many values of the null, because we just make the null of the night hours, a day, and the celebration day and the weekends, and then we just throw it the null data, and so as you see that it's close to the bell curve with the and main consumption is about 125 watts. It's the bigger one, yeah. Then we just take the external data of the temperature and we add one more feature, it's a hourly temperature, because we think that the power consumption of the building depends on the temperature. We just again do some necessary stuff, just grab the data, extract the columns with temperature, and add the temperature to our big data frame. And you see, so now our data frame with time have the huge, it has about 175 columns. You see, the last one is temperature. We just create the histogram of the temperature and see that in Russia most of the temperature is around 0, and also between 10 and 20 degrees Celsius degrees. And we create the huge data frame with all our necessary data. So what we do next, we just try to observe, can we just use the target sum or target sum complex. It's same data but counted of different formula, and you see the mathematical stuff more or less it's same. So we will use the target sum complex counting of the long formula. So then we will do this task like a time series creation. We create the function which is take our data sets and create the vector of our feature and targets. And as you see, we need the two additional value. It's a look forward and look backward. So look backward, it's for how many times we look backward in our case in hours to make the prediction, and look forward, it's for how many hours we will create the prediction. So you get the point. And then we have the function which is create the train and test to splitting our data, because in time series it's we can't just mix the parts, because we can leak the future data in our prediction. We just create our own function for the train test splitting. What we do next, we just for the sake of the using, we just flip the columns. I create the columns of our target from the first column. Then we create the list of our features, because the 175 features is too much. We just create all the we just read all the necessary stuff. We just leave the target our target value, and we leave all the stuff, the accumulator, the power buffs of the users, and external grid, roof, and number of the week, day, week, month, and the temperature. And we and finally we from the 175 feature we choose only the 31 features. So, and you see, and we create the big data frame with 71 feature, one target, and about 20,000 rows. So what we do next, we just again to check does our target feature have the good math stats or not, and we just create the plots again just for the sake of the complete of the observing does everything good or not. And then we just do the do the stuff with the categorical feature, because we have in our data frame data of the switcher which switch on and off the consumption of the roof. We just do the simple one-hot encoding. And finally, we create the data frame. So the 32 columns, it's 31 is the features and 1 is the target. And then we do some, it's not magical stuff, but it's totally necessary stuff. Because we will use the deep learning model and all our data with unscaling, we just create the two scalars. It's a min-max scalars which scale our data in range from 0 to 1. And we create the one scalar especially for the target feature, and we save this scalar in file. We need it for the later work, and we scale all our huge data frame with another scalar, and in the way that our data frame became to the NumPy array as array with the scaled value, as you see here, the first row of that array. So at that time, it's now not the data frame; it's a multi-dimensional array, and we just to observe our feature list from the columns. It's just for the sake of the understanding what we will do next. Here the feature list, it's a feature what we can choose from our data frame, but because we have the NumPy multi-dimensional array, as you see, all the columns have just the numbers, and we just take all the feature, and we just count it of the number, as you see, from 1 to 32, because 0 it's our target feature. And look forward and look backward, it's hour, so it's point in hours for how long we will look of the future, and for the backward look back, so we for how many hours we will look back, it's 2 weeks, and we make the prediction of the 1 week in the hourly base. And we just to create our vector of the features, it's x vector, and y vector, it's a vector of our target. And here we have the look forward, it's 168 points. It's mean for the 1 week we have 168 hours, and we will observe look back for the 336, and we have here the shape of our stuff, and then we train and then we split our data to the train and test. You see. And then we will do our magical stuff, the deep learning stuff. For that problem, I will use the sequential model with the LSTM, and I also try to compare with the GRU units. So we will use the recurrent neural networks. And because in Keras we have it's normally built MSE, the loss function, but in that particle task we will use the root mean squared error loss function. I just write it by my own, and I compare all these two models, which one will be best for the time series prediction. And I will use the callbacks, and as you see, it's early stopper, it's waiting about 40 rounds, and if the validation loss didn't change, it's just shut down the training. And reducer, it's like scheduler, is just reduce of the factor of 0.1 the learning rate if the of the 20 epochs the validation loss does not change, and the checkpointer just create the checkpoint if it will see that the validation loss became smaller than previously. It's just write the weight of our model. And here we just create our model, and here the necessary parts just the count the units. I choose the three one. One was 256, 512, and 768 units. Number of features and how many features we will have in our models, and drop rate. So other stuff is not more or less important, and also don't forget to just notice what's the error function you will use. Here's our model. It's about 2 million parameters, but maybe it's too much because I use all the models, and previously I will use model with only less than million parameters. But so and then we will start our training. It's as you will see, it's 100 epochs, but our model will not train all the epochs because we have early stopper and all the callbacks. And in our case, our model trained about less than 300 epochs, and you will see every epoch was 24 seconds. But if I will choose the units, not the more than 700, but if I will choose the 200 units, every step will have about 4 or 5 seconds. And if I choose it 500 units, every step's about 10 on 8 seconds. And after the training, we have the graph of the loss, and you will see that how it's going, and finally it's just make the plateau and stable. And here the prediction of the weeks of prediction of the 1 week of the hourly based, and you see the blue one is true one and orange one is prediction one. It's not so bad as I was expected. And here it's not the full graph, and here the graph how we can compare the previous and future, and how we will see. And the more interesting thing that I can that I would like notice that as you see, our model more or less clearly understand when the stops, when the night hours, when the weekend hours, and you see our model more or less correctly predict that it will have 0, because from our task description, we don't need the power consumption of the night hours. And then I create the special function for the counting error for the 30 days. I just, for the sake of the visual explanation, because it's not so good to see the error just for the 1 day. I just take our test vector x and y, just divide of the 24, and these errors based on the 30 examples, I mean for the 30 days. And you see that different model have the different laws. The best one was GRU units with RMS prop optimizer with RMS-E errors. You see that it has more than less than 2% the final you see. But the model with 70-100 units train too much time, honestly. It's not worst, and this kind of the model have the 268 units, and it's trained extremely fast, more than less than about 50 minutes. And this model it's trained more than hour and a half. And you see that the difference between the errors not so much, not so drastically changed. And then I create just for the testing of the how our model will work from the cold start. I create the model from the scratch. Just download the weights of this model and make the prediction. I just create the new function which will use only this model, and you see the error more or less the same. Then I create a small data frame for the prediction value and real value and the time, because we just need to see how it's going, yeah. And you will see that they're about less than 3%, yeah. And the next one, we will do the post-processing of our prediction, because we just want to eliminate the night hours, weekends, and so on and so forth, because our models it's good, but not as good enough as real value zero prediction. We just make the zeros all the data which in weekends and out of the working days, and we just create a small filters and apply it. And you see that the errors create a little bit less. It was 208 and became 250. 85, and you see that our model is good enough to predict when the night hours and when the weekend hours and when the celebration day. So thank you so much. It takes me about half an hour to describe what I will do. So thank you for your time, and see you soon. Bye.